Greg.
Georgy Manucharyan.
Oh, okay. Yes, we can see your slides. So it's Gregory Manucharyan from University of Washington. What? Oh, Georgy. Sorry. Sea ice modeling with an explicit representation of the flow life cycle.
All right. Well, thanks so much for inviting me over. And I'd really love to be there with you, but I have a 5-month-old daughter with me, so I'm taking care of her. All right, so towards the end of your day, I'm going to talk about CIS modeling, and really just this is not really state-of-the-art kind of climate scale modeling, but this is more of a talk that will rethink a little bit what it is to do discrete element modeling for media that is discontinuous, but also for media that where you can grow ice and weld it together into bigger pieces. So this just to acknowledge our funding agencies. So ONR was very gracious to fund some of the crazy ideas that I've been having. So thank you for those folks. And this is the project that we're funded on, and postdoc who has been helping a lot with the development of this model is Brendan Montemura. So shout out to Brendan. And Dimitris Giannakis is our PI on this project. Right, so I think for this audience, it's probably needless to say that CIS is at very fine scales, at flow scales, is a discontinuous media. And would like to, well, at least in this talk, to figure out how to model this kind of messy field. When I started looking into this project, I had a look at what kind of models do we have that could model discontinuous media. So discrete element models is one of the way to do that, and this is the way forward for us, at least. But conventional discrete element models, they are looking kind of like this conceptually. So you have a bunch of elements that could be infinitesimally small, or they could have some sort of circles or some sort of shapes to them, and they're bonded to represent bonds between those elements that can break and be created and things like that. And eventually you can come up with equation laws that would simulate the motion of each individual particle. And this is the different types of models that we have, the output that you can get from those. I'm going to criticize those a little bit, but don't get me wrong, I love simplifying things a lot. And having a flow to represent a sort of collection of flows is all great. But I think it's also important to have a model that can present something that looks like observations look. Just sort of when you compare the outputs of this model, you see a bunch of circles, and here you see a bunch of, maybe squares, but something doesn't match up with how CIS looks like visually. This visual mismatch actually is translated to mismatch in characteristics statistically. So how to improve on these models and what can we do? The goal I had in mind here is that let's have a look at this image, for example, of CIs, and just ask ourselves, well, how can we model these CIs? Is it really a collection of bonded points? Maybe yes, if you're a mathematician, but if you're sort of looking at this, I see chunks, which are a set of solid objects, and those solid objects can basically fracture and create some sort of lines at the fracture locations, or piecewise continuous lines. The transition that I decided to make is saying that, all right, we're going to model ice as a collection of polygons. Not a big deal, you think, but headaches start right away. Before you even start figuring out how things move, if you say that, okay, the advantage of having polygons is that I can fill any kind of domain with any kind of flow size distribution that I want to 100%. And as you conveniently have a look at previous talks, that packing these things, for example, to 100% is a challenge of itself without effects in flow size distribution. So for example, if your flows are all the same size, you can't pack it to 100%. So what happens here is that if you have some elements over here and then you start growing new ice, these empty areas where you have just ocean without ice, those areas are quite complex topologically speaking. So there's a lot of holes in them, like over here. And then when you start growing new elements, you're either going to be stuck with putting a whole bunch of tiny flows around it to make sure that you're filling all the gaps, and that affects flow size distribution, or you have to create a flow which is bizarre shaped, like this flow ends up being bizarre shaped because before that it was sort of surrounded by a whole bunch of other flows. So meaning that all the simplicity with using sort of point particles or spheres or disks to model sea ice is gone if you really want to have sort of nice control over flow size distribution, or sort of freedom over having any kind of flow size distribution. So that's a kind of minor headache, but for me it was a major because I'm not an expert in this stuff, so I had to figure this out. And eventually, what ends up happening is that you have a polygon which is non-convex, so it can have multiple collision points with another polygon. But sorting out these issues, you can, in a conventional discrete element way, write down all the forces that act on the polygon, and these could come from atmosphere, ocean. There's some collision forces plus some parameterized forces from unresolved physics, like missing flows, that in a lot of those models, you never model 100% concentration. So you can provide this feedback from unresolved flows. And you can do the same for torques to figure out the rotation of all of these things. And this really formulates a sort of dynamical core of the model, where you have basically solid elements that are colliding with themselves. So one extra thing that makes ice look like ice, and that's kind of the simulation here on the right of the Nares Strait over here, to demonstrate that effect is the fracture flows. So the idea is that you can have relatively large chunks coming in over here, and then this is the ice that's been piled up sort of through over Canadian archipelago, and it's moved like this, and it comes through Nares Strait, and some of it goes to Front Strait over here. But as the sea ice goes through narrow constriction, this is a nice experiment to demonstrate that the flow size distribution is changing because the flows are getting smaller and smaller. So we, in our model, the elements can fracture and they can become smaller in size, and this is what demonstrates it. And this is a case study where we can compare the behavior statistically of how ice moves through this constriction. So one thing that we can plot is the mass transport. So this one here is a function of time, is the mass transport, and you see it's quite discontinuous. So this blue line is basically jumping a lot. That's where you have an indication of this called jamming behavior. That's where a bunch of flows are sort of hugging each other and forming something like a bridge that just holds all the stresses and prevents the flow upstream, the flows from upstream to move downstream. But then when they collapse, then you have strong jumps in mass transport. And we can have a look at area flux, which is just a derivative of this, almost accounting for the thickness of ice as well. So the area flux is something that people have observed in Nares Strait from satellites, and we can compare those. So on average, the observations show area flux of about 0.1 in these kind of units of thousands of kilometers square per day, and this is what we have as well. And this is kind of qualitatively, it looks fairly good when you compare the fluxes, but also we're happy that quantitatively the average flux for the average winds that we prescribed makes sense. So it's not off the chart weird. So now for the things that is actually unique to our model, and a lot of models, discrete element models, will struggle to define even these kind of quantities. But flow size distribution in our model is defined very easily because our model is a collection of actual flows, polygonal elements which have areas and size, and you can define it. And as time goes, the flow size equilibrates to something of a power law, and it is a power law in some regime, some limited range. So you can't have a power law going all the way from 0 to infinity, because that integral would not converge either this end tail or this end tail. But there is some sort of inertial regime, in quotation marks, of a power law that's being established, and our model is doing it. The power here of about -2 is consistent with what people have been observing in Nares Strait. Before that, so basically the simulation that I showed, this is somewhat straightforward in a sense that when I conceptualized the development of the model, I thought, all right, like this is for sure we can do. And if we're lucky enough, we can get all these things by tuning of various types of fracture rules and collision rules, etc. So I think that that part was a sort of 100% solid part. Now, this part is the one that is actually was quite interesting to me, whether this is achievable or not. So this is basically saying that, well, we start, and all the simulations start with some sort of distribution of flows. However, I'm interested in the actual equilibrated distribution of flows, something which has not been affected by humans prescribing initial conditions. And this is, in my mind, is a simulation of winter sea ice. So when you start, let's say, from an open ocean, you don't have any flows, or you maybe have some low concentration of sea ice that eventually grows, and after many, many collisions, you start forming a flow size distribution, and the shapes of the flows and how they look like basically is a question mark, right? So it's something that a model can simulate. So to do that, we have to prescribe a few extra processes such that we can have welding, where you have two flows that are in contact and there's cooling conditions that are satisfied. You can say that they can form one bigger flow. You have fractures, which you talked about as well, but you also have rigid rafting. This is where you can have one flow sort of exchange area and volume with another flow without being bonded in the end. Or maybe it will be bonded if welding happens at the same time. So to do that, here's some crazy loop in the simulation. So this is just for you to envision the complexity of what we're doing. This is basically saying, all right, so you start off with some sort of conditions, you do your coupling with atmosphere and the ocean to figure out the stresses that act, external stresses that act on the flows. Those are the driving mechanisms for the motion. Then you have to identify which flows are colliding with which ones and figure out collision forces. Then you update their position, then you prescribe all this parameterization over here that are changing the shapes of the flow. So the rigid, rafting, fracturing, welding, all of this change the shapes of the flows. Then you do some thermodynamic growth, and then you have to do something with the shape because the shape gets infinitely complex. And it's like geometric growth over here, which is really terrible. So you need, because you can have basically fractal shaped flows, which perhaps are realistic, but they're a headache to model. So eventually we'll bypass this problem to do some flow simplification, and we can calculate our Eulerian mean representational state, and then we do it over and over again until we get something like this. This really is kind of akin to your baby starting to walk kind of moment, because the simulation doesn't blow up, surprisingly enough, and it converges to something that is fairly accurate statistically speaking, and I'm going to show you it in a bit. But this is how the snapshots look like. So you start with some dark ice over here, meaning that it's kind of low in thickness. And these flows, they are somewhat regularly shaped over here. This is because it's still close to initial conditions. And initial conditions was us prescribing Voronoi flows over here. As time goes by, you start creating a complete mess because there were a lot of collisions, a lot of welding events, a lot of fracture events. And eventually you get, after about a month or so, you get some state that looks like that. And you can say, well, this may look like ice, may not look like ice. I don't know. To me, this looks more like ice than previous discrete element models. But just for reference, if you look at SAR image of winter sea ice, that's kind of where we're aiming to get. And there are some things we can fix about it, but just roughly speaking, this is kind of looking like sea ice now. So let's quantify a bit, maybe because, you know, looking like sea ice is not really a quantitative metric, but we can look at ice thickness distribution now and flow size distribution of an equilibrated sea ice model run, right? So this is something that is quite difficult to do with many discrete element models because they're just too computationally demanding. But here we sort of exchange the complexities, and in our model we can do this kind of seasonal simulations. So ice thickness distribution is you just take each element over here, calculate its thickness, and right away you have the answer. So you start off with something like a delta function because we initialized all the flows to be the same. But after a couple of weeks, you see the purple line over here, that's the week 5 model simulation, and there's a best fit gamma function because some people theorize that the ice thickness distribution should be a gamma function. But like it or not, these are the observations over here in January or in February from this Quark's paper. And this is the pale line over here. So the idea is that we're reaching observations, you know, roughly looking pretty quickly. And this is to say that we're using doubly periodic boundary conditions, and we're just prescribing a cooling flux that just cools and grows sea ice up to 100% concentration all the time. So it's a very idealized set of conditions, and yet we are converging to something that looks realistic in terms of ice thickness distribution. Same thing happens with the flow size distribution. We again have a sort of range over here where you can fit the power law if you want. And the power law that we're getting for this winter case is slightly steeper. It's to the power 1 of -3. Looking into some of the recent papers, -3 is in the range of what has been observed for sea ice, especially in packed areas. So just in the interest of time, I'm going to show very briefly a simulation of non-isotropic fracture rules. So the previous simulation that I showed basically ignored the fact that we have these formation of linear kinematic features, and we have non-isotropic fracture patterns. And turns out this is probably for ice budget and for flow size distribution and for ice thickness distribution. Those things don't really matter. But it does matter for predicting the motion of ice, and regionally, if you do care about statistics of these kind of linear kinematic features, you must simulate them. And this model does that too by means of using bonds between the elements and fracturing both the elements and the bonds using some sort of stress-based fracture rules. And there's a whole bunch of theory on how you would on different ways of fracturing stuff. So this is just one example to demonstrate that in a uniaxial compression case, this kind of model can generate a fairly good-looking distribution of linear kinematic features. But again, some more concrete analysis here is needed to demonstrate or to like fine-tune it to actual observations. So to summarize, and I presented this model that does something that other discrete element models don't do. That is the elements of the discrete elements of this model that we call SubZero. They can change their shapes in response to welding, in response to fracturing, in response to ridging. And their shapes are becoming very complicated. So that's why I guess nobody else is doing that kind of work. But I think this gives a certain degree of realism to this discrete element approach that is very relevant to specifically sea ice, where this is a media that is not just fracturing and then that's it, you stop caring about it. No, it's fracturing, and then the new ice is going to form in these open areas or in those leads, and then it's going to consolidate, so it's going to weld together. And all of these processes need to be represented if you want to have a sort of side-by-side comparison or a snapshot of ice with a snapshot of a model simulation. So I think my claim is that this kind of thing might be necessary to do when we really want the realistic sea ice. So the paper is under review, but you can download it from this archive over here. And there's a bunch of endless work that we're trying to do to figure out how to use such a model in situations which could cover the whole entire Arctic Ocean. And those include superparameterization, those include rescaling the interaction laws to go from individual polygons to clusters of polygons to speed things up. Machine learning is one idea that we're going after, is to infer the macro scale rheology. So in the context of superparameterization, this is also quite relevant. And finally, of course, we need to do a whole bunch of validation studies. So if you're interested in, and you have some data sets of sort of concrete processes for sea ice, which you think are simulatable using this kind of model, please do let me know. We'd love to collaborate. So I'll finish here. Thank you so much again for inviting me, and looking forward to your questions.
Thanks very much, Georgy. So any questions?
And thanks a lot. Sorry. Thanks a lot, Georgy, for the very nice talk. I was wondering, how do you handle when you're welding two flows of different thickness? Do you have a heterogeneous flow, or do you move the thickness around to have a uniform thickness?
Yeah, great question. So we, at the moment, there are two ways to do it. So one, we can homogenize the flow, and it's kind of a resolution issue. So you can say that if you're not interested in having heterogeneous thickness of flows, just homogenize and conserve the volume. That model runs fast. Another way that we have is we have subflow idea. So this is where you oops, hold on. Okay, slide stop sharing. Hold on. So subflow idea is basically saying that we're going to treat this polygon as a solid object, but if, let's say, it has another flow welded to it, we're going to keep the information of the piece that was welded. So in the end, you can have your output will be like a solid polygon, but with an area distribution of different thicknesses in it. So it's an option in the model that you can switch on or off. If you switch it on, it kind of runs slower, but it's possible.
Any other questions? No.
Thank you, George. I'm Phil Huang. Actually, I had a presentation of 2 presentations ago. I guess. So you mentioned about the validation of your model, and I'm just wondering any ideas on, and if you don't mind, we can work together in somehow to develop the validation program together. So just sort of about any specific area or any ideas on that.
Yeah, so that would be absolutely fantastic if we could think about it together. So this model is easier to fine-tune or validate if we choose like certain regions that would target certain processes, right? So for example, this Nares Strait I chose is because we can observe flow size distribution sort of at the entrance to Nares Strait, and then we can observe the same or the altered flow size distribution as the sea ice moves through the Fram Strait. And then, since the motion occurs on fairly short time scale, just maybe an order of like a week or so, we can just pretend that thermodynamic processes are not really there, and it's all just mechanical fractures. So in this case, if we have observations of basically flow size distribution, sort of in the Lagrangian sense, as the sea ice is moving through these narrowing areas, then we can try to constrain fracture laws. Another thing that happens is that we can look at collisions of flows and figure out how things fracture. So there's coastlines over here, and for example, when this big flow is going to reach over here, some sort of island or a chunk of a coastline, it's going to fracture into many pieces. And we can basically have a look at even finer scale, where you just have one flow colliding with, say, another flow or a coastline or an island, and figure out how this collision splits it into many different chunks and constrain the fracture rules that way. And then for thermodynamics, I'm proposing to look at ice thickness distribution, especially in how it changes seasonally. So we have these observations from satellites of, well, estimates of flow thickness from satellite. And there is this PDF over here, and I just plotted it for February, but in reality, it has a strong seasonality to it. So when you go, you can have double peak when, for example, you start forming new ice and you still have the old ice over here. And just constraining the ice thickness distribution for this kind of winter simulation will also do good to figure out the welding probabilities, and so basically, yes, the welding parameterizations. And then finally, the important parameterization somehow to think about is ridging. So for ridging, I think this process will be important to describe like the spatial distribution of thickness over here as the sea ice is being pushed to this Canadian archipelago over here. That's kind of where the ice is thicker because the winds are just pushing the ice towards the coastline. And ridging processes there are, ridging and rafting, I assume, are quite relevant, and perhaps they will be the dominant term to describe the thickness of ice there. So we can maybe have a look at spatial distribution of thickness going sort of away or towards the coastline, kind of perpendicular, and see how, in response to winds, this thickness profile changes. So that one will constrain on average what we think the ridging parameterization is. And of course, like, if you have more ideas, let me know as well.
Okay, well, I think it's time to bring it to a close. And thank you very much, Georgy. And perhaps we can thank all the great speakers for a wonderful session.